This is a very interesting number theory problem. It looks kind of complicated, however, the solution teaches us a very important and valuable lesson in mathematical problem solving. So let's get right into it. We have, for positive integers n, we define f of n to be equal to the floor function of n divided by 9. Now, in case you are not aware, the floor function of x for real numbers x basically returns the greatest integer less than or equal to x. So, for instance, floor of 1.5 is equal to 1, floor of 2.9 is equal to 2, and floor of 4 is equal to 4. As you can see, the greatest integers are less than or equal to whatever the input is. So that is the definition of the floor function. Okay, and we also have f to the b of n to be equal to f of, so on and so forth, f of n, where we apply the function f b times. Now note that b is not an exponent, okay? This basically means functional composition b times. Okay, so now that's out of the way, the question is, for how many n smaller or equal to 50,000 are there such that f to the b of n is divisible by 4 for all positive integers b? Now take a moment to digest what this means. Basically, it means that it's asking you how many positive integers n smaller or equal to 50,000 are there such that f of n, f to the 2 of n, f to the 3 of n, and so on and so forth, infinitely. So basically, any positive integer up there. Basically, it's asking you how many n are there such that all of these will be divisible by 4, right? For all positive integers b. Now that might be a bit of a challenge, because how are you supposed to compute all of these values and track if they are, divisible by 4? So how can we approach such a problem? Now, when you're given a tough problem, it might be a good idea to start with some small examples. So maybe you can try some small examples for n and then play around with these two definitions, just to get a feel for them. However, I'm going to start with something that might be a bit unexpected. I'm going to treat the function as if it was given to me as floor of n divided by 10. Now you might be thinking, okay, where did you get this from? What in the world gave you the motivation to consider this function? I mean, you were given this one, division by 9. So why are you considering division by 10? Firstly, division by 10 is very easy. Just move the decimal point over. However, the real insight, I don't really want to spoil it. It has to do with the property of numbers when you divide it by something. And soon enough, you'll see that considering division by 10 is kind of like a stepping stone to realizing that property. I don't really want to spoil it that much right now. Just follow me through. Just bear with me for now. The real insight is very cool, I promise you. So we're going to start with some small examples. So maybe n is equal to 1, 2, 3, 4. Now I know this isn't very small, but it will suffice as a simple example. So we can plug this into the function. So that's f of 1, 2, 3, 4. And over here, this would be equal to floor of 1, 2, 3, 4 divided by 10. And then over here, this would be equal to floor of 1, 2, 3.4. And the floor function brings this down to 1, 2, 3. And there we go. Now, what about something like f to the 2 of 1, 2, 3, 4? Well, this over here is equal to f of 1, 2, 3. Oh, sorry, not 1, 2, 3. 1, 2, 3, 4. My apologies. So, this over here, f of 1, 2, 3, 4 itself is equal to 1, 2, 3. We just calculated that. So this is equal to f of 1, 2, 3. And this will be equal to, this 1, 2, 3 divided by 10, that's 12.3. Floor function, that's 12. Okay, now what about something like f to the 3 of 1, 2, 3, 4? Well, this is equal to f of f to the 2 of 1, 2, 3, 4. Right, that's 1. Now, finally, well, at least one more time, I'm just going to do it one more time, as I said, f to the 4 of 1, 2, 3, 4. Now this, I'm going to skip the details. You can calculate this to be 0. Now, do you see what's going on? I mean, sure, each time you plug the number into the function, you might have done the actual division and then, you took the floor function to get your values. But do you see what's actually going on? Well, notice that at the start, we had 1, 2, 3, 4 as our number. But then we only have 1, 2, 3, and then 1, 2, and then 1, and then 0. So do you see what's going on? It looks like as if we are just chopping off the digits going from right to left, right? As this b value gets larger and larger, we're just chopping off the digits, and eventually we have 0. Firstly, from what we see, it seems like large values of b won't really be of a big concern because they will just be 0, and 0 will obviously be divisible by 4. But do you see what's actually going on with the number? We also conjectured that what we're actually doing is chopping off the digits going from right to left. And that's actually true. Because if you take some random integer like 5,789, I literally just made this up on the spot. If you take this random integer and perform this function over and over again, so therefore raising this b value, if you do it over and over again, notice what happens. Basically, division by 10 basically moves this decimal point over. And then the floor function takes away the fractional part. And then if we do it another time, so raise the b value by 1, we're basically, again, moving the decimal point over and then chopping off the fractional part. And this just continues on, right? And eventually we'll hit 0. But we're just chopping off the digits going from right to left. We don't actually have to do any actual division and floor function. So notice that that's why I switched to 10. Because I wanted to see, what does this function actually do? What does a number divided by something and then floor function actually do, apart from the literal calculations that we see? Okay, but you might be thinking, okay, this is division by 10, but this is division by 9. Well, notice that the reason that we're able to move the decimal point is because we're dealing with numbers in base 10. And in base 10, when you divide by 10, then obviously you can move the decimal point over. But if this is true in base 10, then this would also be true if you considered everything in base 9. If you consider n in base 9, then suddenly this function, and combined with this, is basically chopping off the digits going from right to left in base 9. So why don't we convert everything n into base 9? Because we're converting everything into base 9, I'm also going to convert this 50,000, our upper bound, into base 9 as well. So here it is. Now notice that I wrote a 9 over here to indicate that the numeral is in base 9. If I do not write any subscripts like this one, then assume that it's in base 10. So we've already discovered that if we take a base 9 numeral, like this one, so A, B, C, D, and then base 9, if we take this numeral and perform these two operations on it continuously, then the overall effect is the same as canceling the digits going from right to left. Now, notice that the problem statement basically requires that the numerals A, B, C is divisible by 9, as well as A, B, and A. You can also look at it in another way. The numerals formed by the digits that are before the last digit must be multiples of 4. They must be divisible by 4. So it would also be very helpful if we were able to derive a property that, base 9 numerals have in order to be divisible by 4. Well, to do that, we can actually start by considering the general form of a base 9 numeral. So if we take the general form of the expanded base 9 numeral, so that's a bundle in base 9 times some digit in base 9, and this just goes on, right? So different bundles of different levels. We have the general version of an expanded base 9 number. If we take this, then what can we deduce about it? Well, we're considering divisibility by 4, so it might be helpful to consider this number in mod 4, right? Now, because we're dealing with mod 4, we can actually subtract each of these 9s over here by 8, because 8 is a multiple of 4. So this would become 1 to the n times dn plus 1 to the n minus 1 dn plus so on and so forth, 1 squared d2 plus 1 times d1 plus d0. Now notice that all of these 1s, they're just 1s. So this is literally equal to dn plus, oh sorry, this is dn minus 1, sorry. So dn plus dn minus 1, and then plus dot 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 d2, d1, d0. Now notice that we've deduced that this entire base 9 numeral is congruent to the sum of its digits. So a base 9 number is divisible by 4 if and only if the sum of its digits in base 9 is also divisible by 4. We're going to consider the general base 9 numeral, where all of these are basically digits in base 9, okay? And this is in base 9. So again, just to be clear, this is not multiplication, these are digits in base 9. Now, because we've covered this, because all of the numerals formed by the digits before the last one must all be divisible by 4, we can start by deducing that dn itself must be divisible by 4. And you can write this as dn is congruent to 0 mod 4. Now you might be thinking, what if it's just a one-digit number? But that's a very easy case. So let's glance over that for now and consider this case where we have more than one digits. So this over here, dn is congruent to 0 mod 4. It's true. And we also have dn plus dn minus 1 to be congruent to 0 mod 4. And that's because the numeral formed by dn and dn minus 1 must also be divisible by 4, and that means that the sum of the digits in base 9 is congruent to 0 mod 4. Now, because dn itself is congruent to 0 mod 4, this would mean that dn minus 1 itself must also be congruent to 0 mod 4. So we can deduce that dn minus 1 itself is congruent to 0 mod 4. And again, if you were to consider the numeral formed by dn plus dn minus 1 and dn minus 2, if you consider this, it must also be congruent to 0 mod 4. And you can see that because dn and dn minus 1 themselves are congruent to 0 mod 4, then this would mean that dn minus 2 itself, so dn minus 2 itself must be congruent to 0 mod 4. And you can go like this continuously until you deduce that literally every single digit that is before the last one must be congruent to 0 mod 4. Basically, they are multiples of 4. All that's left to do now is to consider casework, whether if n has 1 digit, 2 digits, 3 digits, and so on and so forth. Now, the maximum number of digits is 5, because the upper bound over here has 5 digits, so it cannot exceed 5. So, case 1, what if n only had 1 digit? Well, in this case, the singular digit would not matter, because when we take the floor function after dividing by 9, it reduces this down to 0. So if it only had 1 digit in base 9, then this singular digit can be anything from 1 to 8. So there are 8 options. And note that this cannot be 0 because, well, the question required n to be positive. So what if we had 2 digits in base 9? Well, this units digit has 9 options from 0 to 8. And yes, it can be 0 this time because it's 2 digits. So we first have 9 options, and then times something, so because we're not done. Now, this next digit over here has to be a multiple of 4. Now, in base 9, digits which are multiples of 4 include 0, 4, and 8. But this cannot be 0, right? Because it's 2 digits. So we must have 4 or 8. So that's 2 options. Now, what about 3 digits in base 9? Well, again, this unit digit has 9 options from 0 to 8. And then this one can be 0, 4, or 8. So there are 3 options. And then this one over here only has 2 options because you cannot have 0. So there are 2 options, right? Times 2. Now, what about 4 digits in base 9? Well, this one over here, again, 9 options. And then this one and this one both have 3 options from here. So 3 squared And then this one over here, 2 options, 4 or 8, so that's times 2. Now, we are on to our last case. What if we have 5 digits? Now, this one you have to be a little bit more careful because we cannot exceed this number in base 9. So it's not like all 5-digit numbers in base 9 will work. So we might want to first consider this number over here. This one, if it's 8, then that's no good because that will exceed this, this number. So this digit over here must be 4. Right? So it must be 4. Now, after we've set this as 4, this number will never exceed this, right? So this one has 3 options. This one also has 3 options. This one also has 3 options. And this one, well, it can be from 0 to 8, so that there are 9 options. And there we have it. This is what we've counted each case, and now we have to add them all up. Our sum will actually turn out to be 485. So there are 485 numbers or positive integers n below this number, which was 50,000. There are 485 of those numbers which satisfies the property that f to the b of n will be divisible by 4 no matter what b is, right? So that's the answer to our question. The answer itself might be satisfying. However, the problem-solving technique was the most important part. Observe that in this case, even though the notation might have looked a bit heavy, might have looked a bit complicated, we tried to analyze these definitions to see if there was really something simpler going on. Thank you very much for watching this video. If you found it interesting, then please do consider dropping a like and subscribing. Thank you very much. Bye.